This is a loaner from the IT department. And so I'm back to recording. And we're recording now. But it does have some disadvantages. The screen is smaller, so I don't have as much room to write. And not only that, the part of the screen it allows me to write on is very much smaller. So therefore I have to write really tiny on this, but it shows up bigger on that because of the magnification. So there's a little bit of a disadvantage there. There are also, well, some of the modes that it operates are a little different. It does upload faster, so that's on the positive side. All right, now where we left off last time, we had just started 4.8, and I think we're about to do example 1. Is that where you had it? Before I get into that, though, let me go over. There are some changes this week. Change number 1, office hours. First mini-term, I had a physical science class that started at 1:15 on Tuesday, Thursday. My linear algebra ended at 12:15 on Tuesday, Thursday. So I had 1 hour of office hours, from 12:15 to 1:15, and that was also my lunch hour. So that was the only time I was in the office for any length of time between 8 in the morning and 5:45 in the evening. Okay. However, this is now second mini-term. I'm starting a second, another physical science class, Physical Science 2, but the main reason I even offer these on mini-terms, I don't like offering science courses on mini-terms. They're too fast and furious. But I have to because the automotive program needs Physical Science 2 for their program. And some of the students, I think it's the GM students, all the automotive students in those three programs, GM, Ford, and Toyota, are on co-op programs. They're in school for 8 weeks. They're on work dealership for 8 weeks. The first year students are in school the first 8 weeks, dealership the second 8 weeks, second mini-term. Second year students are at the dealerships the first mini-term, and on campus the second mini-term. Those are the guys coming back who need the Physical Science 2. However, their automotive programs, because of courses they have to take with them, they go until 3 o'clock, which means I can't start my Physical Science 2 class until 3:15. Now, the good news on that is that now I have office hours on Tuesday, Thursday from 1:15 to 3:15 that I did in the first mini-term. So starting today, I'm in the office from 1:15 to 3:15. However, the downside of that is I'm here until 8 o'clock at night, okay? Whereas before I was here until 6 o'clock at night. But that's okay. All right. Number 2, tomorrow's office hours. Normally they're Monday to Wednesday, 3:15 to 5:15. And that continues. Except tomorrow I've got to go to the Birmingham campus right after my differential equations class is over. Head to the Birmingham campus because we've got a meeting there from 4 to 5. So I've got to be off campus tomorrow during my office hours. Sorry about that. Another thing, and I'm preaching to the choir here because all of you I think have turned in, or maybe all of you have turned in. Possibly most of you have turned in your first test. Okay? Probably sometime this week, they probably are going to open, it may already be open now, midterm progress reports. On the midterm progress report, I have to report anybody who has a D or an F at midterm. And if I don't have a score in, it has to go down as an F. Not that it really matters that much, but you may be getting a call from somebody about getting assistance, okay? I think that's about all, so let's get on to trig. Any questions on what we've done so far? All right? Now, We introduced last time what it means to solve a right triangle. Do you remember what that was? You remember what that was to solve a right triangle? Does anyone remember what it meant to solve a right triangle? Say again.
What do you mean?
Okay. Okay, here I'll give you one. Here's a right triangle. Let me get my pen set up. Okay. Let's just imagine that's a right triangle. Well, that's not very well drawn, but forget that. We are given that this is vertex A, this is vertex B, and or angle A, B, and C. Now, one thing they already told us, a lot of times, excuse me, okay, a lot of times angles are given Greek letters to represent them. But quite often in right triangles, and in triangles in general, they will use capital letters to represent angles. Okay? And in this case, A is this angle, B is this angle, C is the right angle. In a right triangle, C is always the right angle. Okay? Anyone know why? Say again? Exactly. The corresponding side for A is the opposite side. And we give those lowercase letters, A, B, and C. And traditionally, what does C always represent in the right triangle? The hypotenuse. So we've got to have capital C being the right angle because the side opposite that is the lowercase c. Okay. In this problem, they told us that angle A was 34.2 degrees. Now, mine's not drawn to scale very well. Okay? They also told us that B was equal to 19.4. Okay? This is the classical setup. Excuse me. This is the classical setup for a right triangle. They typically will give you one angle and one side. Okay? That's enough to solve the triangle. So what do you think they mean by solving the triangle? Say again? Okay. Solving the triangle means finding the values for the other letters. For capital B, capital C, little a, and little c. That's what we mean solving the triangle. And how do you know B right now? The sum of the angles of the triangle is 180, any triangle, including right triangles. And what do we know about one of these angles? Okay, C is 90 degrees. You know that, okay? That's what that means. So this is 90 degrees, okay? So therefore, B is, there's a name for it, a complementary angle to 34.2, to A. Because if the sum of the three side angles are 180, one of the angles is 90, the other two have to add to 90. That's the definition of a complementary angle. So what would be the complementary angle for 34.2? A little louder? 55.8 degrees. So you've already answered two of the things. This one was almost given, though they didn't say it. This is almost as easy. You just subtract that from 90. All right, now what do? We've got two more steps to solve the right triangle. Cosine of A, that's fine. What is cosine of A? A little louder, I couldn't hear. Adjacent over hypotenuse, which is B over C, right? But we know what A is 34.2 degrees, and we know what B is, 19.4. All we don't know is C. So how can we solve that? Divide by what? Okay, actually, I like to solve for a variable, get it in the numerator. I don't like them in the denominators. So let's get C. Now there's two C's here. That's the little c. Multiply both sides by C. That'll wipe out the C there. And divide both sides by cosine of 34.2 degrees. All right. Is it Terrell? No. Huh? Jawan. Taylor, got it. Yeah. All right. We're now up to 4. What did we start? 16, 17 stitches. All right. So, the cosine 34.2 divides away on this side, and that leaves us with, I'll carry it over here, C is equal to 19.4 divided by cosine of 34.2 degrees. Now that's something you're going to need to use a calculator for. I can't do that in my head. I wouldn't even come close to doing it in my head. So pull out your handy dandy calculators and see what you get. A little louder. 22, you said? 23 point what? 46. I'm going to round that to 5. Now, what you say? Okay. Does this answer make sense? What you get? 425? 45. Okay. Does that answer make sense? Okay. Here's at least a little bit. Because your B was 19.4, you know the C has got to be greater than B because it's the hypotenuse. So to have C as 23.5, that makes it reasonable anyway. About 23.5. Now what do we do? We've got angle A that was given. Angle C was basically given. Angle B we calculated. Side B we were given. Side C we just calculated. All we need now is to get what A is. Little a, side A. How do we get to do that? Okay, very good. You have at least 3 options that were all fairly simple. One is doing the sine of 34.2 and doing that to be A over C. Now the only little issue I have with that is that this was a calculated value. If we made a mistake here, we're going to carry the mistake there. So I like to avoid that if I can. Sometimes you can't avoid it. We could use tangent of 34.2. We were given that. What is tangent? Opposite over adjacent. A over B, we were given B. So that's the one I would prefer. You can use the other. You should get the same answer. But this way, you avoid propagating any error you may have made in that. So let's try it that way. There is a third way too. Well, I'll talk about that. Tangent of, because I don't have much room, I'm just going to plug it in. 34.2 degrees is equal to the opposite A over the adjacent, which is B, 19.4. So this gives us A is equal to, multiply both sides by 19.4. And that wipes out that. So A is equal to 19.4 times the tangent of 34.2. What do you get that to be? 19.4 times tangent of 32. This is Taylor, right? No, you're in here. I'm just trying to find you. There you are.
With the test, you need it sometime this week, right?
I'm sorry?
The first test, you need it sometime this week.
Yeah, it's been due, so anytime you want to turn it in, I'll take it.
When you give out the second test?
I did last time. Okay, so let me get Taylor marked here. Now that I found her. Okay. Yeah, I've been accepting the first test. In fact, there are only 1, 2, 3 people who haven't turned it in. Papers, several have turned that in. I think about 6. So I'll take those anytime. And a second test I passed out last time. Do any of you need that?
I got that last time.
What's that?
I said I got it last time.
Okay.
What time are you here tomorrow?
I'm here tomorrow from 7:45 in the morning until, well, I've got a meeting on the Birmingham campus, so basically 3:15 tomorrow. Most Monday to Wednesday till 5:15. But tomorrow I've got to go to Birmingham, so I'll be here.
I'll be at the Birmingham.
Oh, you will?
Yeah.
I'll be there from 3:15. Well, no, it'll take me 30 minutes to get there, so about 3:45 until about 5:15. But I'll be in a meeting from 4 to 5. So, if do you know where Dr. Pruitt's office is? Okay, you know the B hall, the big long hall on the backside of the quad. The end of that building, the upper part, there's a down floor and an up floor. The main floor, the upper floor. If you come in from the gym, baseball field, tennis court side, come up that half flight of stairs, when you get to the top step, the door immediate to your right is B122. That's Dr. Pruitt's office. If when I'm on the Birmingham campus, my office is the copy room behind the secretary's desk. So if I'm not back there, you can give it to her, and she'll give it to me when I come back. Okay. Miss Rose Saxton, the secretary. Okay. Now, if she's not there, if it's before 5 o'clock, slide it under the door. If the door's locked, slide it under the door. She's usually there, so go in. If I'm not in the back, give her and I'll get it when I get back from the meeting. Okay. B122. Do you know any of the offices around there?
I've seen some. Not really.
You have? Okay, well, I was just going to say, if you knew any of the instructors who had offices there, I'll tell you how close I am to their office.
Your voice is
You know, Mr. I don't know any of it.
Your voice.
Yeah, I went to the UAB football game Saturday. Sorry. Okay. Whitney's here, and Cheston's here. Okay. Did someone need the second test? Okay. graph paper? Do you need graph paper?
No,
You got graph paper. Does anyone else need test 2? Everybody got it? Okay. 1 through 9 are on graph paper. Okay, you got graph. Yeah. And the rest on there, just answer. Okay. Justin came in. All right. Anyone else come in Cicero Road? Got it. All right. Did anyone give me the answer here? Side A is 19.4 times the tangent of 34.2 degrees. So again, 13.2 approximately. Okay. Does that make sense? What you think? Yes, it does, because it's the side opposite the smallest angle, so it should be the smallest side. Sure enough, it's smaller than 19.2 and 23.5. So that's making sense. So there were 3 ways, at least 3 ways we could have approached side A once we knew the other stuff. One was through the sine of 34.2, so that would have involved using a calculated quantity rather than a given quantity. Tangent, you can calculate it just using the given quantity. Can anyone think of one other way we could have gotten side A? Anybody? Second, Pythagorean theorem. 23 squared minus 19.4 squared will give you a squared. So the square root of 23.5 squared minus 19.4 squared. But again, that would have used a calculated value and a given value. The way we did it used both given values. So as precise as we could get it, that should be it. Let's see how the book got. The book got 55.8 degrees for B. They, of course, had that C was 90. They started off with a tangent of A, coming up with A equals 13. Now they said 13.18. I really find that a little disgusting because they're given quantities, 3 significant digits, 3 significant digits. So how in the world do they get 4 significant digits for their answer? You can't do it physically. I mean, it just doesn't pan out that way. Okay? You can write down as many digits as you want to, but you only have 3 significant digits. That's why I rounded to 13.2. And that's also, and then they did C, and they did C the same way we did. Yeah. And they got 23.46, which to me rounds to 23.5. Okay? Because you can't get more precision out of a problem than you put into the problem. It's kind of the reverse of garbage in, garbage out. It's good stuff in, that's as good as you can get out. Okay. By the way, folks, there are checkpoints after just about every example, so please, when you get home, do the checkpoints. All right. Here's example 2. A safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. And I'm not even sure I want to get on the ladder that's at 72 degrees. That is a pretty steep ladder, okay? The fire department's longest ladder is 110 feet. What would be the maximum safe rescue height? Maximum safe rescue height. What would be the first thing you would do on a problem like this? Draw you a picture. And thank goodness they drew one. There it is. Okay? So I don't have to draw it. Okay? Now, were reading that problem, I would assume that that ladder would be from the ground, okay? They have it on top of the truck. I think I'd rather have my ladder on the ground. But anyway, your maximum angle of elevation, 72 degrees, and the longest ladder, 110 degrees. What we're looking for is what? Is it this B down here? No. If they say, how far from the building should they park the truck? That B would be of interest. We're not interested in that. We're looking for the maximum safe height, which would be A. So, given what we know, given what we know, the angle here is 72. We assume here, there's an assumption, two assumptions, that the building's on level ground, and most of the time it is, and most of the time, unless this happens to be in Pisa, Italy, and you happen to be a certain famous tower, most buildings are perpendicular, okay? So we'll assume that we're perpendicular there. So here's our picture, 72 degree angle, 110 degree hypotenuse. We're looking for side A. How do we determine what the maximum safe height is? Help me. How do we determine A? Sine of A is equal to what? Little a over C. Opposite over hypotenuse. Well, we know capital A, that would be sine of 72 degrees is equal to little a we don't know, but we do know the hypotenuse, which is 110 feet. Now, you don't have to carry the units around. So what I would do is multiply both sides by 110 feet. I'm just going to write 110 because I don't have room to write feet. And that should give us approximately what A is. Pull out your handy-dandy calculators. Make sure you're in degree mode and do your calculation. What do you get? Say again. 110 times sine of 72 degrees. Say again. Okay. Okay, in the book, they also said 104.6. Okay? And you said 105, right? It said maximum safe height. I'm not going to round up. I'm going to either leave it just what it is or round down. I would say 104. I know rounded it would be 105. If I'm on that ladder, I'm leaving my fingerprints embedded in it. Okay? No. But maximum safe, don't round up, round down. You always err on the side of safety. In an esoteric math problem that doesn't really matter, yeah, round the way you're supposed to round. This one, I would have said 104. Okay? Above the fire truck. So you have whatever height it is above the fire truck. If that ladder were on the ground, it would be 104. Because you can't go any higher than that. Now, you might also say, you might be able to rescue someone from a little bit above that, but I wouldn't say so. Those people are scared to death. Okay. Any questions on that? They have a checkpoint with that one too. I would definitely go home and work on it. Or you don't even have to go home. Next possible opportunity, work on it. So let's take that away and see how they did it. from the equation that sine A, exactly the one you used, is equal to the opposite A of the hypotenuse C, then you can solve this for A. Now they're solving it literally, and that's perfectly fine. Multiply both sides by C, and you get A is equal to C sine A, then plug it in. I either call it plug and chug or chug and plug. This is the chug and plug. The way we did it with plug and chug. It doesn't really matter. Okay? Chelsea, right? Yeah. I was just finding you. Okay. And when they did the math, they got 110 times sine of 72 degrees, be sure in degree mode. And they came up about 104.6 feet. If I'm on that ladder, I make it 104. I'm not going to risk anything beyond what I can safely handle. Okay. So the maximum safe rescue height is about 104.6 feet above the height of the fire truck if it's mounted on top of the fire truck. All right, they skipped example 3 and 4. So let's do examples 3 and 4. Do 3 first. At a point 200 feet from the base of a building, what's your first step? Draw pictures. So as I read this, I picture things. So number one, I'm going to assume we're on fairly flat level ground, and we got a building going up here, okay? And we're 200 feet from the base of the building. So let's say this is 200 feet from the base of this obscure building here, okay? The angle of elevation to the bottom of a smokestack. So this building has a strange smokestack that sits up right there on the edge of the building. So the angle to the bottom of that smokestack is 35 degrees. Okay? Whereas the angle of elevation to the top of that smokestack is 53 degrees. It's shown in the figure here. Now they drew theirs reverse side. They even have smog in the air, so you can tell it was a smokestack. No, I'm just kidding. Okay. That's what was given. Find the height S of the smokestack alone. So this is what we're looking for, S. Is there anything in this problem that enables you to calculate S in one step? Excuse me. Or how would you approach the problem? We want a height there. This first piece of information they gave you, 200 feet from the building, angle to the bottom of the smokestack is 35 degrees. That tells you basically nothing about the smokestack. What does it tell you? What can you get from that? The height of the building. So that would be, what do you want to name that? Anything special? Say again? Okay. All right, good one. Okay, yeah. What we're going to do, let's give a name to this. A. Okay, that's what the book used too. A. So We're going to call angle 35 angle A. Okay? 53, we're going to have to come up with a new name, but we'll get there. So, first thing I would suggest is calculate little a. And what would that be? You know, angle A and 200 feet from the building. Tangent, okay. You get that little a, well, okay. Tangent of 35 degrees is equal to what? A over 200, okay? Because it's opposite over adjacent. So multiply both sides by 200, if I could write, 200 feet. Okay, cancel out the 200s, divide them out, whatever. So A is approximately 140, about 140 feet. Okay. Now, looking at the picture the way we've drawn it, what can you tell me of another relationship? The bigger view, angle 53. Yes, and we use tangent again, so we can say the tangent of 53 degrees is equal to A plus S over 200, right? Got it? Multiply both sides of the equation by 200. What does that give you? A plus S is equal to, second, 265. Okay, but we already know A, that was 140, so let's subtract A from both sides, and that gives us S. The length of the smokestack, which is what we were looking for, is equal to what? About 125 feet. And somehow they got 1/10 of a foot out of it, 4/10 of a feet. No, you can't do that. If you only have at most three significant digits here, you only have 2 here and here. You really could argue you can only get 2 significant digits, possibly 1, because that 200 foot. I'll let you get by with a whole number. Well, you can get anyway if you want. But I would round that to 125 feet. They got 125.4. Okay. Again, this problem does have a checkpoint. Any questions on that? Do you see how to do it? Break it into pieces. Handle. Have I asked you this before? How do you eat a 5,000-pound elephant? One bite at a time. So when you're solving these problems, do every little bit as you come to it and put them together. You can solve the whole elephant then. Okay? All right. There's one more, example 4. All right, to erase this before I go on. Okay, example 4. I apologize about my voice. It's just getting worse the more I talk. But
The UAB win?
yeah, by 2. It was quite a good game. They Middle Tennessee State University, who was supposed to beat them handily. And the previous week, or sometime previously, they beat Louisiana Tech, who was supposed to beat them handily. So,
How many games have they won?
they're 4-2, I think. Yeah, they were supposed to be last in the league, and right now they're probably tied for second or something like that. So they're doing quite well. I think he's a really good coach. All right, let's do example 4. A swimming pool. I think you know how to start this one, don't you? Draw your picture. It's 20 meters long. Like this is 20 meters long and 12 meters wide. Okay. Jim? All right. By the way, before you leave today, if you didn't pick up the second test, be sure to get the second test. Okay. I passed it out last Thursday. All right. 12 meters wide. Well, this is sort of a two-dimensional drawing, and my two-dimensional drawings are supposedly a three-dimensional drawings. They're not very good. Okay? The bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end and 4 meters deep at the deep end. Okay? As shown in the figure. Find the angle of depression in degrees of the bottom of the pool. So here supposedly is the bottom of the pool. So what the angle of depression is the angle below the horizontal here. What do you want to name that? Anything special? Second? Theta? Sounds like a good name. Okay? Now, if you drew the rest of this, which I really don't want to draw, but I will do it. That's not very good drawing. Okay, whatever. Okay. What we want is the angle of depression. How do we proceed to get it? How do we proceed to get it? Say it again. Tangent of theta is certainly going to be the trig function I use because we're interested in this angle. We're given this, and we're given that, and we're given this. Okay? So how do you use tangent of theta in that context? What is tangent theta there? Say again. And what is your opposite then? Not quite. I can't hear. 2.7. The difference of 4 and 1.3, because this is your 1.3, so this will be 2.7 is your opposite side divided by 20. Be sure you keep everything in meters. Okay? If one was in feet and one's in meters, you got to convert. So, can you tell me what theta is? Say that one more time. Divide by what? We don't know the angle, so we don't know the tangent, right? Okay. We've done inverse functions, right? That's how we do it. To get theta alone, you take the inverse of both sides. And that would give you theta is equal to the inverse tangent, or arc tangent, of 2.7 over 20. How you undo a tangent is take an inverse. Not divide, take an inverse. So, if any of you gotten that, be sure you're in degree mode, because they said they want it in degrees. .7 degrees. So we have theta is approximately 7.7 degrees. Angle of depression. They rounded to 7.69. How they got that much precision? When the max you got is 2 here, 1 or 2 there, maximum of 2 there. How could they get 3? They can't. So 7.7, I find, is the better answer. Good deal. There is a checkpoint there too. I would definitely give a look to it. All right, any questions on that? Now, you know what we call the width of the pool, 12 meters? Extraneous information. You did need that for the problem. And you're advanced enough students, you probably didn't even bother with it. But I remember when I first started teaching, I was adjunct instructor at Jeff State. I was teaching Math 090. And there was a problem in the homework. We bought a box of 48 cookies for $1.19, and you bought 3 boxes. How much did you spend? Well, I had some students, the student rule is conservation of information. If they give you the information, you've got to use it somewhere. So some of them had done something with it and multiplied by 48 cookies. Why, I don't know. And had you paying $70, $80 for those 3 boxes of cookies. Or they divided by 48 cookies and had you paying a fraction of a penny for the 3 boxes of cookies. Without asking, do these make sense? No. 3 boxes for $1.19 each, multiplied. The 12 meters was given. It's not used. Don't feel like you got to use it. Y'all didn't. Very good. All right. Let's go on. Now, trigonometry and bearings. Okay? These are not the little round gizmos that are in wheels to keep friction from happening. That's one type of bearing, but it's not what we're talking about here. What we're talking about here is things like relative bearing or directional bearings. In surveying and in navigation, directions are often given in terms of bearings. However, you got to change your mindset a little bit. Because up to now, when we were given an angle, where do we think of measuring that from? The positive horizontal axis. Okay, so up to now, we've measured all angles counterclockwise from the positive horizontal, right? That's how we do it in trig. That's not how we do it with bearings. A bearing measures the acute angle that a path or a line of sight makes from a fixed north-south line. So now we're measuring from either up or down. We're not measuring from right, okay? For instance, if you had this as a bearing, south 35 degrees east, That means you start going due south, and then you go 35 degrees toward the east. So you have to get north, south, east, west. You have to know your directions here. So south, 35 degrees east. Always an acute angle, either from north to or south, going to east or to west. Okay? And that's what you would have here. South, 35 degrees to the east. Okay? This would be north, 80 degrees west. Okay? What would this one be? North 45 degrees east. Very good. Any questions on that?
The first one always be north to south?
Second?
Would the first one always be north to south?
Yes, the first is always north or south, then the angle, and the last is always east or west. So the first tells you which way to point, and then the next one tells you how far to point and what direction. From there. Yeah. Okay, so you have to sort of turn around your thinking and make sure you draw pictures. All right, here's example 5. And Tyrell decided to show. He was listening in the back. A ship leaves port. Port is over there at A. There's the port. Very straight beach here. And it's leaving point A. At noon. And heads due west at 20 knots. Okay? By the way, does anyone know what a knot is? K-N-O-T. It's not something you tie in on a string. It is, but what is a knot in this context? It's a nautical mile per hour. What is a nautical mile? Yes, but it's not the same as a mile on land. A mile on land is 5,280 feet. A nautical mile is 6,000 feet. So a nautical mile is a little bit longer than a statute mile. Okay? So that's what we mean. 20 nautical miles per hour. NM. That's really an unfortunate abbreviation. If we were in the metric system, that would be nanometers. Okay. Not nautical miles. A lot of difference between a nanometer and a nautical mile. At 2 p.m., the ship changes course to north 54 west. So this is its new course. Now, they didn't give its original course because it was due west. You can't say north or south. All you say is due west. Okay. Now, it says find the ship's bearing and distance from the point of departure at 3 p.m. Okay. So what we had leaving here at noon, traveling 20 knots, 20 nautical miles per hour, due west for 2 hours, because it said at 2 p.m. it changed course. So it traveled a total of 40 nautical miles west, and then still going 20 nautical miles per hour, 20 knots, it went 54 degrees north 54 west here, and went another 20 miles here because it's 1 more hour between 2 and 3. So 20 nautical miles there. What we're looking for is the ship's bearing and the distance from the port of departure at 3 p.m. How are we going to do this? This is not a single step problem, by the way. So what do you reckon we need to do first? Okay? Because the tools in our tool belt now a restricted right triangle trig, right? We don't know how to do it with an angle like this. So what we're going to use to get a right triangle out of here, we got two of them. One here, from that point to here, and one here, from this point to here. There's a right triangle. So we're going to use this right angle twice. Okay? Now, in the first case, we know this angle here. That's not in each one of these right triangles, right? So what do we have to do? To use this right triangle here, the right angle here, we need this angle. So how do we get this angle from that angle? Anyone? So again, complementary angle to 54 degrees, and what's that? Subtract 36? Yeah, 36 degrees. So there's our first step. Figure out this is 36 degrees. Okay? So we know this side here, which happens to be the hypotenuse, and this angle. So we can first calculate how far we went here. They call it distance B because they said this is A, B, C, D. Okay? So they call this distance B. So let's find out how long that is. How do we do that? Cosine of 36 degrees is D over 20. Very good. There's our relationship. Cosine of 36 degrees is equal to D over 20, which means that D is equal to 20 times the cosine of 36 degrees. In other words, multiply 20 by both sides. And that gives you D is equal to 20 cosine 30. What do you say? 16? Okay. 16 nautical miles. I see that and think nanometers. It's not nanometers. So D is 16. Does that make sense? Yes. It's got to be less than 20. Yeah, 16 makes sense. Okay, so we'll call that D 16 nautical miles. Okay? Now, we need something else. In order to use the big triangle, ACD, to get side D, C, that's what we want. We want that side C. That's one of the things we want. Okay? We need to know this length here too. How do we get B? Sine of 36 degrees is what? No, sine of 36 degrees in terms of our sides here is what? Say again? B over 20. Opposite over hypotenuse, which multiply both sides by 20. So that gives us B is equal to 20 times the sine of 36 degrees. And what did you say that was? Did you say 11? Is about 11 nautical miles. Okay? Now, okay, time out here. When we were dealing with our round-offs, that's only for final answers. Most of the time, I'm going to hang on to as many digits as I can when I'm doing the internal calculation, and then at my final answer, round off. Otherwise, when you round off every step of the way, you're introducing what they call round-off errors, and they can expand on you. So when you have it in your calculator, leave it in there. I'll write it down this way, but you leave it whatever this length was and that length was. Leave it in there as many digits as you can, okay? If you have to erase it, store it if you need to. 11 nautical miles. In reality, keep those decimals. Second? No, I don't want to write them down. Okay. Just hang on to them. Okay. Now, what do we have? We have, for the big triangle, whose side is C, which is one of the things it's asking for, the distance from the point of departure to where the boat is at 3 p.m. That's what C is. To get that, we use the big one, which is 40 plus 16, which is 56 nautical miles for this side, 11 nautical miles for this side, and where do we go from there? How do we get C? Second, Pythagorean theorem. But now I would use all those digits you had, and what do you get C to be? So C is approximately the square root of, what do we say, 56 squared plus 11 squared. But you give me it in your best effort. Has anyone done it? Have you done it? What do you get C to be? Anything? $57? Approximately 57 nautical miles. Does that make sense? It better be longer than this side because it's hypotenuse. This is 56, that's 57. That makes sense. Certainly it's longer than 11 or whatever this was. So yeah, that seems reasonable. So that gives you the distance from the point of departure at 3 p.m. How about getting that bearing from the point of departure? Can anyone give me the letters? Maybe not the number, but the letter. North, west. I need an angle in between that. The bearing is going to be north something west. What is that angle going to be? Well, I'll draw it in for you. It will be that angle right there, right? But our triangle is not going to give us that angle. What angle will our triangle give us? This angle. How can we get this angle from our triangle? There's several ways. Give me one of them. Not Pythagorean theorem, I don't think. That's how we got to 57. How do we get this little angle here, this little acute angle there? Little acute angle. You want me to put it in a different color? What color? Huh? Red? Okay, that'll show up pretty well. So this is the angle we're looking for now. What would we use to get that angle? Then we can subtract that from 90 to get the one we're really interested in. What would give us the red angle? By the way, the seagull's gone. Let me take it off. What's that? Sine of what? Of what? Sine of A. Sine of A, okay. I'll write it down up here. Sine of A is equal to what? B over C, right? Is that what you said? That certainly is one way to get it. Sine of A is equal to B over C. We calculated B, we just calculated C. Whoa! That was a lot of calculations there. We calculated two things to get C, and then another calculation to get the sine of A. We had one calculation to get here. If I had my druthers, I might go with the tangent. This will work. But the tangent will be this over this. At least that contains something we had to begin with. But let's see. Let's use the sine of A. And what do we get? Sine of A is B over C. That would be 11 over 57 approximately. And A would be that. How would we get the angle A? Inverse sine. So angle A would be the inverse sine or arc sine of little b over little c. Someone tell me what that is. It's about 11 over 57, whatever that comes out being. Are y'all following? Doing? What you get? Say again. 11.9. So let's call it 12 degrees. Okay? What will be our final answer then for the bearing? That's not the bearing. That was the little angle, red angle there. The bearing is this one, and what would it be? 90 minus 12, which would be 78 degrees, approximately. So north, 78 degrees west. Okay? You know, we came out pretty close, didn't we? They had 57.4. I don't see where they got that precision. And 11.82, we got 12. Okay? Pretty good. Okay? That's how we did it. Let's see how they did it. From the triangle that we had before, this is how they started. We started out with the 54 degrees, subtracted from 90, got 36 degrees. Okay? Then the two sides of that triangle can be determined. The hypotenuse was 20, so the side B was 20 times the sine of, no, that was the side here. The sine of 30, 20 times the sine of 36. D was 20 times the cosine of 36. They came up to be, wow, they didn't even list them. And then they said tangent of A was B divided by D plus 40. So if they put 20 sine 36 over 20 cosine 36 plus 40. They were letting the calculator hang into all those digits they could. Okay? And when they did that, they got a number, then an arctangent, and they got radians. Why did they go to radians? That makes no sense whatsoever. Because guess what? This problem was given in degrees. But they went radians, and then they came out 11.842 degrees. I would have rounded that to 12, which is what we did. Okay? The angle with the north-south line is 90 minus that, which would be right at 78 degrees. Okay? So the bearing of the ship is north, 78 degrees west. Okay? From the triangle ACD, you have that sine A is B over C, exactly like we said. C would then be over sine of A, so they chose the same angle you did. That would be D sine 36 divided by sine of 12, 11.82. They gave you 57.4 nautical miles. All right. Any questions on that? Again, they have a checkpoint there after this one, bottom of page 32. And unfortunately, I can't believe it, we're out of time. Yeah, get over it. Okay. Okay. So we'll be starting next time with harmonic motion, the top of page 333. This is a long section. Okay. Hopefully we'll finish this next time. Homework exercises here include any of the odds 5 through 13, either 15 or 17 or both. Any of the odds 19 through, through 45. I will do some of these. There's some length problems, some height problems, some distance problems, some angle problems, design type problems, speed enforcement, navigation. So do a few of each of those. Okay? Through 45. We'll pick up with 47 later. Before you go, anyone who did not get test 2, the second half of chapter 4 test, I've got them here. They're not due until we finish chapter 4. So, until a week after we finish 4. So probably will be due a week from Tuesday. So you can get started on them now. When you get them, tell me whether you need graph paper or not. No, you don't want to keep that. You need graph paper?
Do I need what? Graph paper?
Graph paper.
Yeah.
Okay. I'm going to give you 2 sheets, front and back. There's 9 to graph, so if you do 2, 2, 2, and 3, you should get it. You need graph paper?
You didn't get back to the test yet either.
No, not everybody's turned it in.
Okay, I was just asking because I have kids on Thursday.
What?
I was asking because I have kids Thursday and I didn't.
I'm going to try to get the grades on Blackboard today, but they're all graded, but they've been turned in. I'm missing 3. Anyone else need a test? Test 2. Wow.